This presentation focuses on connecting a resistor and inductor in an AC circuit where the components are connected in parallel. So one of the things that we have to remember is that when components are connected in parallel, Kirchhoff's current law is still satisfied. So if I had a number of impedance values which are in these boxes here, and they are connected in parallel to one another, so they're all connected on the top, and then again they're all connected on the bottom, so they are in parallel. That if I had current entering a junction, then the current would split off and go through the different impedance components, but according to Kirchhoff's current law, the current that's entering that junction, which is the total current, has to add up to the current that passes through all the different impedance values. So remember that the impedance values here can be combinations of resistors, inductors, and then we're also going to have capacitors as well. So there's a box here because we don't know exactly what components those are inside. If we apply the equivalent of Ohm's law for impedance, we know that the total equivalent current can be written as the voltage divided by the impedance. So I could take this complicated circuit and reduce it down to a single impedance value connected to a single voltage supply with a current running through it. Because these are connected in parallel, components that are connected in parallel always have exactly the same voltage. So the current that's passing through the impedance, the first impedance component would be the voltage divided by the impedance, and then the second one again in voltage divided by impedance, and so on. And all of these voltages are exactly the same value because they're connected in parallel. So those voltages would cancel out, and I find that impedance values connected in parallel add as the reciprocal. So I could add all of these impedance values together as the reciprocal, and it would tell me what the total equivalent impedance value is, or the reciprocal of that value. So this behaves, impedance values connected in parallel behave like resistors or inductors connected in parallel. Those values add as the reciprocal. And the big difference between just a resistor or just an inductor is that these impedance values are phasors. So I have to treat them like complex numbers when I add them, and I can't just add or add the reciprocal of the numerical value. If I have just two impedance values connected together in parallel, I can solve for the total equivalent impedance by multiplying those two impedance values together and then dividing by the addition of those two values. And this just comes from the addition of two fractions and putting things over a common denominator. So suppose that I have a voltage supply, and that voltage supply is connected to a resistor, and then also in parallel to that is connected an inductor. And that inductor has an inductive reactance of 20 kiloohms. So this source is oscillating in such a way that it creates an inductive reactance of 20 kiloohms in that inductor. If I were to change the frequency of oscillation here, that would change the reactance of this particular component. So we're asked to determine the total equivalent impedance, the current that comes out of the voltage supply, and then the current that passes through the resistor and the inductor. And then we want to sketch the phasors for these currents and voltages and figure out the phase difference between the total current that's coming out of the source and this voltage supply. So in order to figure out the total equivalent impedance, I need to figure out the impedance of each of the components. So the 10 kiloohm resistor has an impedance of 10 with an angle of 0, or just a real part of 10 kiloohms. The inductor has an impedance of 12 kiloohms, that's the reactance of the inductor, and that has a phase angle of 90 degrees, or it has a strictly imaginary part. Because these two components are connected in parallel, I want to determine the total equivalent impedance and it adds as a reciprocal, or specifically if I have only two components in parallel, I can multiply their impedance values and then divide by the addition, and this is a little bit easier than adding as the reciprocal, which we actually will do another example later where we add just using reciprocals. So if I plug in the impedance of the resistor and I multiply that by the impedance of the inductor, and then I divide by the addition of these two values, I can multiply the 10 by the 20 kiloohms, and I'm going to get 200 kiloohms squared. When I multiply the phasors, I add the angles, so that gives me an angle of 90. And when I add the components on the bottom, that just gives me a complex number in rectangular form, and I can convert that into polar form. I can find the length of the phasor by taking 10 squared plus 20 squared, the square root, and I get 22.4. And I can find the angle by taking the inverse tangent of 20 over 10, and I get 63.4. I'm not quite done yet. I need to find the impedance value, so I can now divide 200 by 22.4, and I get 8.93 kiloohms. And I can find the angle by taking 90 and subtracting 63.4, and I get 26.6. So this resistor, 10 kiloohm resistor, and this inductor that has a reactance of 20 kiloohms in parallel are equivalent to a total impedance that has a value of 8.93 kiloohms and an angle of 26.6 degrees. So I could draw a box around these two, and it would have this equivalent impedance, and then it would be connected to this voltage supply. I want to determine the current that is coming out of the voltage supply. So if I want to determine the current, I can take the voltage over the total impedance. I know the voltage is 10 volts, phase angle of 40, and the total impedance is 8.93 kiloohms, angle of 26. If I divide 10 volts by 8.93 kiloohms, I get 1.12 milliamps. And if I want to find the angle, I take 40 minus 26.6, and I get 13.4. So the total current that's coming out of this voltage supply is 1.12 milliamps, and it has a phase shift of 13.4 degrees. I'm also interested in knowing what the current is through each of the different components. So the current through the resistor would be the voltage of the source divided by the impedance of the resistor, and because they're in parallel, they all have that same voltage of 10 volts. So I would divide by the impedance of the resistor, so 10 volts over 10 kiloohms is 1 milliamp, and then 40 minus 0 is 40. And if I'm interested in knowing the current through the inductor, again, they're in parallel, so I would take the voltage going across all of those components, which is 10 volts with an angle of 40, and I would divide by the impedance of the inductor, which is 20 kiloohms, angle of 90, right? This is my reactance, and my angle is 90. 10 divided by 20 is 0.5, and then 40 minus 90 is negative 50. So my inductor has an angle of negative 50. Kirchhoff's current law has to be valid, so I could take this total current and I could add that total current has to be equal to the addition of the current through the resistor and the current through the inductor. This is phasor notation, so I have to treat those as phasors. I can't just add the numbers, which makes sense because 1 plus 0.5 does not equal 1.12. I have to take into account the fact that they have a phase shift. I'm not going to do this here, but we could add those together and check those. So if we wanted to make a plot of what these look like, the voltage is at an angle of 40 degrees in our complex plane. Our current is at an angle of 13 degrees. The current through the resistor is in phase with the voltage across the resistor, which also makes sense because Ohm's law is valid. The current through the resistor and the voltage across the resistor should always be in phase with one another, and they are. On the other hand, the inductor has an angle of -50, so it's below the axis. And one of the things that I notice is that the current through the inductor, compared to the voltage across the inductor, they are out of phase by 90 degrees. And in fact, the voltage across the inductor leads the current by 90 degrees, which it should from what we know about inductors. As we look at this picture again, the total current that's coming out of the source should be equal to the current across the resistor plus the current across the inductor. If you treat these as vectors, as we can with complex numbers, and you connected them head to tail, and you added them together or used the parallelogram method, this total current would be equivalent to these two currents added together. If I wanted to just know how does the voltage of the source compare to the current that's coming out of the source, I realize that the voltage, which is at 40 degrees, and the current that's at 13.4, the voltage leads the current by an angle of 40 minus 13.4, which is 26.6. I'm going to reiterate the fact that the voltage across these components compared to the current that's coming out of the source, the fact that it leads by 26.6 is apparent because if we looked at the total impedance in the circuit, it has an angle of 26.6. That angle for the total impedance tells us that the voltage of the supply leads the current that comes out of that supply by 26.6.